Okay, problem 1-1. On this piece of blackboard, I've just shown how to find the terminal present value u of n in case 1 over here by drawing the payment stream. Now, another way we can find u of n is just quite rigorously use the formula. So what we have from the formula on page 3 is that u of n equals this sum after we have used the fact that the benefits are 0. So u of n is equal to the sum of 1 plus I to the t minus s multiplied by c of s, which is the contribution at time s, for s equals 0 to t. Now what we notice is, well, what is the contribution at time 0? Whoopsie, it's just 0, which means that the term for time 0 actually just disappears. And what are the contributions at the other time points? Well, they're just all 1. So what does that mean? If we think about this sum, the first term where s equals 0 is just equal to 0. So we can start at s equals 1, go up to t. Sorry. Now, I'm making one of my mistakes again. That kind of happens when you're just talking to yourself in front of a screen. Hope it gets better with time. Had to replace the n into the t here because that's what we do when you use n in a function. And the function is expressed by t over here. Okay, great. So it goes from s equals 1 up to n multiplied by I plus 1 to the n minus s. And then I have multiplied by c at time points 1, 2, 3, 4, 5, 6 up to n. But that c is just equal to 1. So that's just multiplied by 1, which kind of just is invisible. Now, how can I use the geometric sum formula here? Well, we can't just really use it yet because I need s to be up here and s to be down here, and that's not the case right now. So what do I do? Well, let us try to think a little bit about this. Let's just try to think a little bit about this. What is actually in this sum? Well, when s is equal to 1, what do I have in the power? Then it says n minus 1, right? When s is equal to 2, it says n minus 2. And then it goes all the way up to n minus 3, n minus 4, n minus 5, and then up to n minus n, which is just equal to 0. So the thing that I can actually do is say, well, wait a second. I can just notice that this sum is the same as the following sum here. If I changed my index to k instead, and then I let the sum run from k equal to 0, which corresponds to when s is equal to n up here, and then it just runs all the way until n minus 1, which corresponds to the term up here where s is equal to 1. And that's very nice because now I can use the geometric sum formula, and then I just arrive at the exact same conclusion as I did earlier. This, right? When I plug it all into the geometric sum formula, this is what I arrive at. So that's all very nice. I have shown the first part of the equality. I want to show the second part, namely that the terminal present value in the case where I have an annuity in arrear is just equal to the initial present value accumulated in periods. Now, what's the intuition behind this? The intuition behind this is also quite simple. It's that when I look at stuff here collectively, well, then that just corresponds equivalently to if I look at the entire payment stream at time 0 and find the value for the entire payment stream at time 0, and then just say, now I have it all in one bag, let's accumulate it all until the end. So intuitively, it kind of, it makes sense. It makes sense. We're not too surprised. But why is this calculatively equal to 1 plus I to the nth multiplied by an? So this part is what we want to show next. And let me do that down here. So this is equal to, let me see, what do we have? Well, maybe it's a good idea if we kind of go a little bit backward. So let's just enter an interlude here. Boom, 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 boom. Okay, so 1 plus I to the n multiplied by an. I kind of want to calculate backwards so that it starts reminding me of this. So one thing that I can start doing is plug in the value of an that I know from its definition, and that value is given by this thing over here. So it's 1 minus v to the nth divided by I. Or I can also kind of notice, well, maybe I don't need to do that, but well, let's just do that first. Okay, so what happens now? I can see that that something funny happens if I multiply this into the numerator, right? Because if I do that, then, well, the first term in the numerator becomes 1 plus I to the nth, and the second term, it becomes 1 plus I to the nth multiplied by v to the nth. And what is v to the nth? Well, what is v? V is the discount factor. V is equal to 1 over 1 plus I. That's the definition of v. So because this is the value of v, then 1 plus I to the nth multiplied by v to the nth, well, I don't know what I've written here. 1 plus I to the nth multiplied by v to the nth, that's just equal to 1. And that's pretty cool because now we've shown the second part of the first case as well. Okay. Now we have shown that 1 plus I to the nth multiplied by an is equal to this expression here, which we have already established is equal to the terminal present value of an annuity in arrear. So just to sum this up, and I will also do the case 2, but that will be in the next video. Because actually I kind of feel if you've watched this, then you can sort of figure out case 2 on your own. But if you still want to see the solution, you can see it in the next video. But let's just sum up. To sum up, Sn, aka the terminal present value of an annuity in arrear, has, well, this is equal to the thing that we calculated, which is 1 plus I to the nth minus 1 divided by I, and also equal to the end period accumulated interest onto, so this times an, which is the annuity's initial present value.